Our presentation is on the General Parallel File System by IBM. GPFS is a parallel file system used to distribute and manage data across multiple servers. It is implemented in many high-performance computing and large-scale storage environments. It is described as a parallel file system because data is broken down into blocks and stripped across multiple disks in an array, then read in parallel when information is accessed. This allows for faster read and write speeds. It is built from a collection of disks that contain file system data and metadata. A GPFS cluster can contain up to 256 mounted file systems. It was designed from the beginning to support high-performance computing and has been proven very useful for a variety of applications. It is installed in clusters supporting relational databases, digital media, and scalable file services. Additionally, commercial applications requiring high-speed access to large volumes of data, such as digital media, seismic data processing, and engineering designs. The GPFS project started as a Shark Video On-Demand project at IBM Almaden Research Center in September of 1991. By March of 1993, the project was expanded to the Tiger Shark, a scalable and reliable file system for video on demand. As for the specifics, Tiger Shark was a scalable parallel file system designed to support interactive multimedia applications, particularly large-scale ones such as interactive television, ITV. Another influence of GPFS was IBM's own Vesta file system, fully established around 1994, which emphasized the idea of file partitioning to accommodate the request of parallel applications that run on high-performance multi-computers with corresponding I/O systems. By 1998, GPFS, renamed to Spectrum Scale, was first made available on AIX, a series of proprietary Unix operating systems developed by IBM for its computer platforms, then steadily made releases for the Linux and Windows Server.
As the name implies, IBM's General Parallel File System is a parallel file system. What this means is that data is striped across multiple disks and then read in parallel. And so if you look at the bottom right, you can see this picture shows, it's a graph of how parallel file systems work. On the left, it shows what it looks like in terms of directory, and on the right, you see how it looks like as a storage. If you just replace server with disks, this is how GPFS works. You have all the data stored as blocks in the various disks, and then it works through a communications network to be accessed by various nodes. Whenever a disk is assigned to the file system, a file system descriptor is written and added to that disk. It is used to identify each disk and its place in the file system. Something unique to GPFS is that the size of data blocks and metadata blocks can be specified and made different sizes. And so in the specific case of GPFS, it uses a shared area network, acronym is SAN, which is used to facilitate the communications between any in-out nodes and the data. Bottom left, you can see this. As mentioned earlier, data and metadata is stored as blocks that are striped throughout the various disks. Each file is made up of data blocks and will have an inode assigned to it that holds the metadata. This metadata holds various things such as permissions, dates, size, file type, but most importantly, it holds pointers to the data blocks. However, since the amount of data blocks will increase if there's a larger file, what can happen is if there's a file that's too big, a single inode will not be able to hold all the pointers to the data blocks. So, what this file system does is it assigns either one or more layers of indirect blocks that each hold pointers to data blocks. And as you can see in this diagram on the right, it shows the inode linked to two layers of indirect blocks in order to fit a file that's too big for just one inode. Since the metadata is striped throughout the various disks in the system, it's distributed very well. As a result, the system is not dependent on a single directory controller or index server. Additionally, the metadata can be separated from its data entirely and placed on an entirely different disk. This improves the metadata performance and Since metadata performance is a source of bottlenecking in workloads, this increase in metadata performance translates to an overall better system performance. In short, General Parallel File System is a parallel file system that does an excellent job in distributing the data well throughout the disks that it is assigned. Because the data is so well distributed, it does not have to worry about depending on some centralized directory controller or index server that might limit the whole structure if it's compromised. Additionally, in allowing the metadata to be separated from the regular data, it can increase the performance of the metadata and provide an overall system performance increase. This makes it excellent for use in very large workloads, where another system might suffer from bottlenecking if the metadata performance is bottlenecked. Furthermore, with its use of indirect blocks in conjunction with its inodes, it can very efficiently store the metadata for the data that it has. This ultimately amounts to a file system that is resilient to failure due to its distribution and efficient in both storage of its metadata and its performance.
Hi, my name is Rohan, and today I'll be covering data allocation in GPFS. Achieving high throughput to a single large file requires striping the data across multiple disks and multiple disk controllers. GPFS implements and manages its own striping in the file system, as opposed to using something like a logical value managed layer, or LVM. These LVMs are very similar in functionality, but they can't adequately balance load like striping can. Striping allows GPFS to have necessary control to achieve fault tolerance and balance load properly. Striping works optimally when disks have equal size and performance. However, if disk is of a non-uniform configuration, a trade-off arises between throughput and space utilization. Having optimal space utilization will just mean more data and having larger disks to store it on. But these larger disks will receive a proportionally larger amount of I/O requests, and this will result in the smaller disks becoming underutilized. GPFS allows the administrator to handle this trade-off however they want, allowing them to balance between space utilization and total throughput at their own discretion. Large files in GPFS are divided into equal-sized blocks. The block sizes are typically very large, about 256 kilobits, but they can be anywhere between 16 kilobits to 1 megabit. The large block size allows for a large amount of data to be retrieved from each individual I/O request to the disk. Smaller files are stored in subblocks, which can be as small as a 32nd of a normal block. When allocation blocks for a file, GPFS uses a round-robin algorithm to spread the data across the disks in the file system. After a disk is selected by this algorithm, the location of the data within it is determined by the block allocation map type. GPFS has two different block allocation map types in a file system: cluster and scatter. For cluster, GPFS attempts to allocate blocks in clusters. Blocks in a file are stored next to each other within each of these clusters. This is a great allocation method in relatively smaller instances. This is the default allocation method for file systems with 8 or fewer disks. The other allocation map type method is scatter. In scatter, GPFS chooses the location of the blocks randomly. It provides a more consistent file system performance by averaging out the performance variations due to the block location. This is ideal as the number of disks increases when the file system is larger or when the file system free space becomes fragmented. Because file systems are typically pretty large, this is the appropriate allocation map type in most cases. This is the default allocation map method for file systems with more than 8 disks. GPFS handles large, non-optimal files with minimal threading very well by utilizing disk parallelism. For example, if a large, single-threaded application is being processed by GPFS, GPFS will issue I/O requests in parallel to the proper number of disks needed. This will increase the rate of reading and writing from or to the single file to match the data rate of the underlying disk system. GPFS can recognize several different access patterns: sequential, reverse sequential, and other forms of strided access patterns.
Replication in computing involves sharing information to ensure consistency between redundant resources such as software or hardware components to improve reliability, fault tolerance, or accessibility. The purpose of replication is improved disk failure tolerance. If some disks fail, as long as at least one replica of all relevant objects is available, I/O processing can go on, even if other replicas are on unavailable disks. Replication in GPFS means having more than one replica or copy of a given file system object. An example of such an object is a user data block, a directory, or an internal GPFS metadata object. When replication is in use, a single logical object may be represented on disks by one or more physical replicas. For example, a file consisting of 10 logical blocks is represented on a disk as 20 blocks when two-way data replication is in use. The level of replication specifies how many replicas of a given object should be created. An approach of the replication in GPFS is a stretch cluster configuration. This configuration is defined over 3 geographically separate sites, 2 production sites, and a tiebreaker site. One or more file systems are created, mounted, and accessed concurrently from 2 active production sites, as opposed to the traditional method of an active and a backup site. With synchronous semantics, all writes are committed to both production sites. To ensure consistency and integrity of data within the file system, GPFS enforces the concept of token management. Each file system has one corresponding file system manager which handles all the nodes within. The designated file system manager node performs the duties of the token manager server. The server coordinates access to files on the shared disks by granting tokens that convey the right to read or write the data or metadata. This service ensures the consistency of the file system data and metadata when different nodes access the same data. The first time a node accesses a file, it must send a request to the token management server to obtain a corresponding read or write token. After having been granted the token, a node may continue to read or write the files without requiring additional interactions with the token management server. This continues until an application on another node attempts to read or write the same region in the file. Normal flow for a token. First is a message to the token management server. Second, the token management server then either returns a granted token or a list of nodes that are holding conflicting tokens. Third, the token management function at the requesting node then has the responsibility to communicate with all nodes holding a conflicting token and get them to renounce the token.
In this section, I'll be discussing how GPFS addresses any kind of errors that may occur during file sharing. As we continue to increase the amount of nodes and disks that are being used, it becomes increasingly unlikely that all components will be running correctly at all times. With this being said, it implies that there is a need for handling component failures. In this section, I'll be discussing 3 different types of failures that may occur and how the GPFS system addresses these issues. The first failure I'll be talking about are node failures, the second, communication failures, and the third, disk failures. When a node fails, GPFS must restore metadata being updated by the failed node to a consistent state, and in doing so, must release resources that are being held by the failed node, or lock tokens, and it must appoint replacements for any of these special roles that a failed node may have. For example, a metanode, allocation manager, or a token manager. GPFS is extremely useful in that it stores recovery logs on shared disks, meaning that metadata inconsistencies due to any node failures are quickly repaired by running log recovery from the failed node's log on one of the surviving nodes. After log recovery is complete, the token manager releases tokens held by the failed node. Since tokens are only released after log recovery is complete, metadata modified by the failed node will not be accessible to any other nodes until it's known to be in a consistent state. After log recovery completes, other nodes can acquire any metanode tokens that had been held by the failed node and thus take over the role of the metanode. If another node had sent metadata updates to the old metanode, but at the same time of the failure had not yet received an acknowledgement that the updates were committed to the disk, it'll resend the updates to the new metanode. Now let's say that the token manager fails. If this happens, another node will take over the responsibility and reconstruct the token manager state by querying all surviving nodes about the tokens that they currently hold. Since the new token manager does not know what tokens were held by failed nodes, it won't grant any new tokens until the log recovery is complete. Tokens currently held by the surviving nodes are not affected by this. The next type of failure I'll be discussing is communication failures. To detect node failures, GPFS relies on a group service layer that monitors nodes and communication links via periodic heartbeat messages and implements a process group membership protocol. When a node fails, the group layer services informs the remaining nodes of a group membership change. This triggers the recovery actions described in the previous section. A communication failure, on the other hand, such as a bad network adapter or a loose cable, may cause a node to become isolated from the others, or a failure in the switching fabric may cause a network partition. Such a partition is indistinguishable from a failure of the unreachable nodes. Nodes in different partitions may still have access to the shared disks and would corrupt the file system if they were allowed to continue operating independently of each other. For this reason, GPFS allows accessing a file system only by the group containing the majority of the nodes in the cluster. Nodes in a minority group, on the other hand, will stop accessing any GPFS disk until they can rejoin a majority group. Unfortunately, there's no guarantee how long it'll take for each node to receive and process a failure notification. When a network partition occurs, it is not known when the nodes that are no longer members of the majority will be notified and stop accessing shared disks. Therefore, before starting log recovery in the majority group, GPFS fences nodes that are no longer members of the group from accessing shared disks. And finally, disk failures. Since GPFS stripes data and metadata across all disks that belong to a file system, the loss of a single disk will affect a disproportionately large fraction of the files. As a result, GPFS configurations use dual attached RAID controllers, which are able to mask the failure of the physical disk or the loss of an access path to a disk. Large GPFS file systems are striped across multiple RAID devices. In these configurations, it's important to match the file system block size and alignment with RAID stripes so that the data block writes do not incur a write penalty for the parity update. Serving as a supplement or an alternative to RAID, as we've discussed in class before, GPFS supports replication, which is implemented in the file system itself. When replication is enabled, GPFS allocates space for 2 copies of each data or metadata block on 2 different disks and writes them in both locations. When the disk becomes unavailable, GPFS keeps track of which files had updates to a block with a replica on the unavailable disk. If or when the disk becomes available again, GPFS brings stale data onto the disk up to date by copying the data from another replica. Meanwhile, if the disk fails permanently, GPFS can instead allocate a new replica for all affected blocks on other disks. Replication can be enabled separately for data and metadata. In cases where part of a disk becomes unreadable, or if there are bad blocks, the metadata replication in the file system will ensure that only a few data blocks will be affected, rather than rendering a whole new set of files inaccessible. In short, GPFS is great for fault tolerance, as it seamlessly works to fix node failures, communication failures, and disk failures. When a node failure occurs, metadata must be restored on the failed node and any tokens held by it are released, appointing replacement and log recovery by another live node. On the other hand, GPFS handles communication failures by fencing nodes that are no longer members of the group from accessing shared disks. Finally, disk failures are detected by the file system manager once it is informed that there is a disk failure by the node that detects it and is marked. GPFS facilitates replication, therefore enabling recovery on disk failures.
General Parallel File System by IBM is an extremely useful and well-known file system that we would recommend because of the reasons discussed in this presentation. The topics we covered today were history, design and organization, data allocation, replication and consistency techniques, and fault tolerance.